Welcome to the Friendly Neighborhood Tutors, where in this video we're going to review Unit 1 of Calculus, and we're going to try to get you to understand all the core ideas as well as understand the math speak behind it. Alright, so let's get into it. Hello guys, welcome to the Calculus AB review, where we review calculus. And this is Unit 1, Topic 1 review. Alright, so first, let's introduce calculus. What is calculus? Well, calculus at its core is basically about finding instantaneous change, and the idea of change occurring over an instant. But if you think about it, how would change even occur at an instant? Well, let's illustrate this with an example, right? Harry Styles is walking on the street, doing whatever Harry Styles does, when suddenly he gets violently hit by a truck in a freak accident. At this point, Harry just goes flying in the air, and he travels like 30 feet in like 10 seconds. Overall, he traveled roughly 2 feet per second. Right? Harry had to go to the ER. But, right, if we wanted to find the velocity at any point, we know that the average velocity is 2 feet per second. But the velocity might be changing from point to point by like drag, acceleration because of gravity, his face pummeling into the earth and it's slowing him down. So how would we calculate instantaneous velocity? Well, if you just approach this like normally, you would just like be like, oh, that's your distance over time, right? But then this is 1 instant. So then if you try to find distance in 1 instant, that's 0. If you find time in 1 instant, that's 0. So 0 divided by 0, well, we don't know how to do that. So that sucks. So let's try to come up with something. Alright? So luckily, math figured out a way. So let's go to math speak. Imagine you have like a function, right? Where you have his position on the x-axis and time on the y-axis, or something like that, right? If you want to find his velocity at any given point, right? Pick the point where you want it to find the velocity, right? Let's say point x, right? And then add a small number h to it, right? For another point, the x coordinate of another point, right? So you have 2 points. Now, if you find the limit as those 2 points, as the distance between those 2 points approach 0, or h approaches 0, and you divide that by the difference in value between them of the functions at that point, that would give us a slope, and what the slope approaches as the 2 points get closer and closer together. So what this means is that now you have a limit that evaluates what the slope approaches as those 2 points converge to 1 point. And now this is how you find the instantaneous rate of change. But how would we do this with limits, right? That's topic 2. So we basically learned that calculus at its root completely relies on limits, right? Because it's all about instantaneous rate of change, and how do we find that? We use limits, right? And so we'll get to how to evaluate the instantaneous rate of change, and we'll get to that soon, right? But first, we need to understand limits to use limits, right? So it's ever so slightly, in a course, completely reliant on limits to define limits and learn how to use them and the limit notation, right? So basically what you need to know for limits and limit notation is that a limit is basically what a function approaches as you have its value approach something, right? So let's say you have a function f of x, right? And we say as the limit of f of x, as x approaches c, so like x gets super close to c, right? What does the limit start to equal, right? Which we write as the value r. The limit f of x as x approaches c is equal to r, right? Let's imagine a situation, right, where it's f of x is 1 over x, right? As x approaches infinity, right, x gets bigger and bigger, right? The overall function equals 0, right? So this is how we write it, right? That's pretty much all of topic 2. Topic 1.3 is basically about finding limits from like a graph of a function, right? So let's walk through some examples. Imagine you have the graph of the function x squared, right? and you're trying to find the limit as x approaches 1. Well, you just sort of look at what the function sort of gets to as it approaches 1, right? That's pretty easy. You can just look at the graph and be like, oh, the graph of x squared at x equals 1 is just 1. So now that's easy, right? But there's sometimes you'll be able to run into problems, right? Imagine you have the function 1 over x, and you have the graph of it, right, centered at the origin, right? What is the limit as x approaches 0? Well, now we have a conundrum, right? From the right side, it like goes up and goes to infinity, but from the left side, it goes to negative infinity, right? Those are two different numbers, so that's sort of a problem. Like, how does that work? Well, that's why we have a concept called one-sided limits, right? Basically, a one-sided limit is like, oh, what does it approach from one side, right? That's how we get around this. So basically, let's say you have the function, like, let's go back to the same one, right? 1 over x, right? What is the limit as x approaches 0 from the negative side? So the negative side is like the left side. So it'll come from the left side, and oh, it's going down, it'll go to negative infinity, right? So the limit is negative infinity, right? Let's look at it approaching 0 from the positive side, or the right side. Well, if we do that, it goes to infinity. So the positive limit is infinity, right? So now we have one-sided limits. That a one-sided limit is just a limit from one side, basically, right? And a real limit only exists if both the one-sided limits are the same. So they both like come together to the same thing, then they're the same thing. Okay? But what if they don't equal the same thing, right? Then we say the limit does not exist. So the limit of 1 over x as x approaches 0 does not exist because both sides don't go to the same thing. They're different, right? Some other reasons it might not be the same is, let's say it's like oscillating or something, right? So let's imagine this function sine x, right? If we try to find the limit as x approaches infinity, we can't do that because it's oscillating. So we don't know what it is at the end because it's just going back and forth. It doesn't converge. That's why that doesn't exist either. The limit as x approaches infinity of sine x does not exist, right? That's pretty much 1.3. So basically 1.4 is basically like, what if you had 1.3, which is basically finding limits with graphs, but instead of having graphs, you had a table, right? So imagine this table right here, right? What is the limit as f of x as x approaches 4, right? As you can see right here, we have like 3.999, and we have like 4.999, or not 4.999, 4.0001, right? And those are like really close to 4. So we could just like say, oh, look at them. Look, the value in between looks like it's 5. So we could just go ahead and call it like that. And that's pretty much like a limit from a table. It's an estimate. It's not exact because you don't know for sure if it's like straight, but you can get a pretty good estimate because they're really close values. I want to pull up sort of an interesting analogy here. Imagine like a limit as sort of like a decryptor, right? If there's a point that you don't know what the value of, right? Or let's say there's like a discontinuity, right? You can use limits as like a decryptor and find that unknown value, or at least what the function like sort of gets to, so you can fill in like the bubble with a good guess. So far we've been introduced to the idea of limits, what they are, a little bit of how to find them, how to use them. So now let's understand the properties of it to better use them. So what are all the things you can do with limits, right? So 1.5 is basically just algebraic properties of limits. So what is that? You can basically just use them like normal numbers almost. Okay, like you can subtract limits, you can add limits, you can multiply two limits. Like you just evaluate each limit and then multiply them. Okay, so like let's say you have the limit of x as x approaches 1 times the limit of x squared as x approaches 2. That's like 1 times 4. There you go. That's pretty much it. You can like also like put them inside one another. You can be like, oh, what's the limit of f of x of f of g of x? So let's say g of x is x squared and f of x is 1 over x, right? What is the limit as x approaches 2? Well, we just evaluate the inner one, right? So what's x squared of 2? That's 4. What's 1 over x if x approaches 4? There you go, that's 4. That's 1 over 4, and bam, there you go. You can start stacking these together and form some pretty complex and crazy stuff and evaluate them, but it's just like a normal math problem. Sometimes when you try to find the limit of functions, like through direct substitution, it gives you an indeterminate form, like 0 over 0. So sometimes you have to algebraically manipulate it a little bit. Most of the time you can just directly substitute, like the limit of x approaching 2 of x squared, that's just 4. But sometimes you have a case where you can't do that, like the limit of 4x squared minus 2x all over x as x approaches 0. If you plug x equals 0 directly into it, you get 0 over 0. So sometimes you gotta factor and cancel a little bit, right? So if you factor it, you can pull out a factor of x and you can cancel it. So you can divide everything by x, so you get 4x minus 2. Now if you plug it in, you see that it approaches negative 2. Sometimes the limit doesn't exist. Like if you the limit of x plus 1 times the x plus 2 divided by x minus 4 as x approaches 4, you can't factor this because so that means you just have to say that it doesn't exist. Now there's also a little bit of memorizing you need to do. There are 4 trig cases that I am showing on the screen right now that you have to memorize. Later in the year we'll show you how to evaluate these without needing to memorize them. You have to use something called L'Hopital's rule, right? And that you can look that up on your own if you want to find that, or because we don't cover that yet. We'll cover that later in the year. Basically, the question might not be as neat and simple as this. Sometimes you have to use these as like foundation and use like trig identities to simplify to this state. That's basically all 1.6 is about. 1.7 sort of relies on 1.8 a little bit, so we're going to skip 1.7 and come back to that later. 1.8 is about squeeze theorem. Yes, squeeze theorem, like how you're squeezing your stress ball because you have a calc test tomorrow and you're just starting to study today. Basically, when you don't have a function that you don't know the limit of, you find a function that's less than or equal to that function and another function that's greater than or equal to the function, right? So if it's greater than or equal at all points and there's another function that's less than or equal to at all points, right? If both those functions converge to a point, then the function in the middle is sort of squeezed and it has to be that point too, right? So let's say you have the limit as x approaches 0 of x squared sine x, right? You know that sine x is in between -1 and 1, right? Those are the extremities, right? So you know that x squared sine x has to be greater than -x squared and less than x squared, right? Because those are the extremities of sine x. That's the top and the bottom, right? And if you evaluate the limit as x approaches 0 of -x squared, that's 0. And it's the same case for x squared, positive x squared. The limit is 0. So that means x squared sine x, since it's in between those two values at all points, it has to be equal to 0. Using this, you can find the limits of functions you don't even know, as long as you know that it's in between two other functions. Those two functions get to a certain point. Okay, so now we can get into 1.7. So what's 1.7 about? It's really just picking the procedure you need to simplify and solve these limits, right? So there's a few ways to simplify. You can do substitution, you can do fact, which is directly plugging in. You can do factoring, which like you factor and then you simplify. You can do the conjugate method, which I'll explain. You can use the trig limits, which are the 4 you're supposed to memorize. You should use, and you can use squeeze theorem, which is what we just learned. Right? Basically, conjugate method is basically when you have like something in the numerator or something in the denominator. It's like a plus b or a minus b, right? And a or b is under a square root. Okay, so let's say you have square root x plus 2, right? So basically what you do is you multiply by the conjugate. So let's say you have the sum of two things. You multiply by the so you subtract the two things. So let's say you have square root x plus 2, then you just multiply it by square root x minus 2, right? And you do that for both the numerator and the denominator, and that's basically the conjugate method. Alright? So when would you use each of the methods that I explained? Well, you first use substitution, just like you gotta try to do it first. If it works, it works. If it doesn't, that sucks. Then you go to factoring, then you try to simplify, you get it, and if that works, then it's great. Conjugate method, you have the sum, or like you subtract two things, and one of them's under square root in the numerator or the denominator. That's when you use conjugate methods. Trig limits is when you have sign or like trig stuff, and the squeeze theorem is when you have like a combination of things and like it just none of the other things work. You have to try to come up with something that lets you find the limit. So we've learned how to find limits from graphs, tables, and equations, and basically what you need to understand is that they're all multiple representations of the same thing, okay? And basically all this topic's about is connecting them. So I showed a few problems on the screen. Now I gave you either the equation, the table, or the graph for these three things. Your job is to try to figure out the rest of the things in this. We'll have the key in 5, 4, 3, 2, 1. There you go. Hopefully you got them. The way you approach this is basically if you have an equation, you sort of just plug in values for the table, and then you get like 3 or 4 of them, and you have a table. And then if you also can just do that for like a graph. You find the 3 or 4 points and you just plot them, and you draw a line in between them and you connect them. And that's basically how you do this. 1.10 is all about exploring the types of discontinuities. But to understand what discontinuity is, you need to know what a continuity is. Right, so let's define continuity at a point, which is 1.11. Okay, basically for a function to be continuous, there's only two things that need to occur. It has to have a limit, and the limit has to equal the value of the equation at that point. Okay, so the limit has to exist, the function has to exist at that point, and they have to be equal. Alright? So what are the types of discontinuities? It's basically some time when that's not true, when those things are not true, right? So there are 3 types of discontinuities you need to know for this exam, but you don't really know. You don't need to know the names. You just sort of need to know them, right? So there's a removable discontinuity, which is a discontinuity where the limit of x from the right side is equal to the limit of x from the left side, right? So there is a limit, right? But the function like jumps at this point, like it like just has a random point for some reason, and it's not connected. There's just like one point that's like off, right? Like here in this graph. Okay, that's removable because you could basically just draw a line through it and ignore that point, and basically it's almost the same thing, right? But yeah, a jump discontinuity is where the one-sided limits aren't the same, right? But the point does exist, right? So like, let's say you have this piecewise function, right? Where they meet and there's a value at every point, right? There's a value at x equals 2, right? But it jumps at this point, okay? That's a jump discontinuity because like it jumps between them, right? And a discontinuity due to a vertical asymptote is the third type, okay? Basically, when you have a vertical asymptote, it's like when the limits from each side approach positive or negative infinity and the point just doesn't exist. Okay, since the point doesn't exist, that means it's a discontinuity, so yeah, those are the 3 types you need to know. 1.12 is all about confirming that a function is continuous over a certain interval, rather than just an individual point. Okay, well, the first way to approach this is, well, first, if a function is continuous, that means it exists. Okay, it has to exist, because that's one of the 2 conditions, right? So that means any function that's continuous over an interval, that means it's that interval is in its domain, right? So we need to find when it exists, right? So when would something not be in the domain, right? Well, let's say like it has a denominator right? Let's say you have a polynomial of x minus 4 over 4, right? The function doesn't exist at x equals 0. It doesn't exist when the denominator is 0, right? Another thing that you have is logarithms, like log 5x plus 4, right? The thing inside the log thing has to be positive because you can't have like log negative numbers, okay? So whatever, like 5x plus 4 that's inside the log thing has to be over 0, right? Another time where this doesn't exist is sec x, cosecant, tan, and cotangent, right? They don't exist at some points because they approach infinity. It's basically like the thing when you have a denominator and the denominator is 0 because sec x, cosecant x, tan x, and cotangent x are just like a combination of sine and cosine that have denominators, right? So and square roots are the last thing. Square roots basically like square root 5x plus 4, whatever's inside the radical can't be negative, like the same thing for logarithms. So 5x plus 4 has to be greater than or equal to 0. This time it can be equal to 0. Right? All polynomial, rational, power, exponential, log, and the trigonometric functions are continuous over their domain. So basically what this means is that if you find the interval and it's one of these types of functions and it doesn't and then the interval lies in its domain, it's basically continuous. The only other situation where you have to check is if there's a piecewise, okay? If you have a piecewise, you have to check if like it meets all the conditions for the interval, and also you gotta check if it meets at that point, okay? First, you just basically have to check that the functions, the limit is the same and that the equation exists at the point where they meet, right? And then if they do, and the intervals on each side are also continuous, then it's then the whole interval of the piecewise is continuous. If they don't meet, or like there's a point that's discontinuous on like another thing in the piecewise, it's also discontinuous, right? For example, if you have like x when x is less than 4, x is less than 0, and 2x when x is greater than or equal to 0 as the piecewise, we can evaluate these both at 0 because that's where they meet, and they both equal 0, so it's continuous over the entire domain that exists, right? They both equal 0, and the function equals 0 at that point, so it's continuous at that point, right? And that means it's continuous over its entire domain, and in this case the domain is infinity to infinity, so it's continuous over everything. 113 is all about removing the discontinuities. Remember in topic 1.6 when I said sometimes you need to factor and cancel to find the limit of functions that don't exist at certain points, like x squared minus x divided by x? Basically this topic is all about that. Basically, if you can cancel and simplify, like you can turn the one above to x minus 1, that is continuous. There is a limit as x approaches 0 for x squared minus x over x, even if the function doesn't exist there, right? So if it's removable, right, if the discontinuity is removable, then there is a limit, okay, if you can factor. And you can say the discontinuity exists at like the x point where it wasn't continuous before, and you can say that the continuity is the x, you can say that it has the coordinates, the x value where it wasn't there, and then the y value is just the limit, right? You can say that discontinuity there. 114 is pretty straightforward. Basically what you need to know is that if there's a limit from the right side or a limit from the left side of a function and it approaches infinity, there is one of two things happening. One, there's an asymptote, or two, the function is unbounded, meaning no vertical boundary. If x is not infinity, it is an asymptote, but if x is not approaching infinity, it's an asymptote. If it is a positive or negative infinity, then it's an unbounded function. That's basically all you need to know. Like, take the limit x approaches 1 from the right side of x plus 1 divided by x minus 1, you get 3 over 0, which if you plug it in, you know it's an asymptote because it goes to either positive or negative infinity from either side, and x is not approaching positive or negative infinity, right? One neat trick you can see if the limit is positive or negative infinity is you can just plug in a value a little bit above or a little bit below the actual value, depending on if it approaches from the negative or positive side, and basically depending on the sign of that, you can tell if it goes to positive or infinity. What does this mean? Let's say the limit x approaches 1 up from the right side of x plus 1 over x minus 1. Since it's from the right side, the value has to be a little bit bigger, so if you plug in 1.001, you get 2.001 over 0.001, which is a really big positive number, so you know the limit approaches positive infinity. For 1.18, basically what you need to know is that if a limit as x approaches positive or negative infinity is not infinity, then the function is horizontally bounded, meaning there is a horizontal asymptote that is y equals something, and that's the limit, right, of the function. It approaches that. It doesn't like just go to infinity or negative infinity. Let's say you have like the function x or x squared or something like that. Then as it approaches infinity, it goes to infinity or negative infinity, right? It like just expands or like goes down. But sometimes you have functions where it doesn't do that, right? So let's say the function 1 over x, right? It approaches y equals 0. If you go really far to the right, then it looks like it's like a flat line at y equals 0. It basically just looks like y equals 0 if you go to the right really far, right? So basically, when is there a horizontal asymptote? For a function with a numerator and denominator, there's a horizontal asymptote of 0 if it's bottom heavy or the denominator grows faster, right? So let's say you have x squared plus 2 over x cubed plus 1. X cubed is bigger than x squared, so it approaches 0, right? If it's top heavy, that means the function like goes to infinity positive or negative infinity, so it's unbounded. If the functions grow at an equal rate, then the asymptote is the ratio of the top to the bottom function, right? So let's say you have 2x cubed over 4x cubed, right? As you approach infinity, it just goes to like y equals 2, right? Y equals 1/2. For most functions without denominators, you should be able to plug in and see what it equals. For trig functions like sine x and cosine x that oscillate, the limit to infinity doesn't exist. But if you have like sine x over x, where the denominator grows faster than the numerator, it still approaches 0. Now for sine x over x or other functions where the numerator and denominator are the same type, it may be more obvious which one grows faster. But for others, like e to the x or over 4x to the 100th power, it's less obvious. So you need to know the order of growth. And this is basically universal, right? Logarithms grow the slowest, polynomials grow a little bit faster, exponentials grow a little bit faster, factorials grow faster. Basically, you know this order, okay? And depending on that, you can look and see which one grows faster. Basically, what you need to know is you have two different types you can compare them using this. Trig functions oscillate and don't grow all the time, so they're not included on this list. So basically, 1.16 deals with the intermediate value theorem, right? So I'm gonna give you an example of how this works in like English and then go to math speak, okay? So imagine you have a function that represents your height, okay? Your height is like continuous, okay? Let's say you know when you were born you were like 1 foot tall, long, whatever, and now you're like 20 or something and you're like 6 feet tall, right? Basically what that means is there was a point when you were 3 feet tall, okay? In between when you were 0 and 20 years old, right? Because you had to go through that to get 6 feet tall, right? So basically, that's basically all this is about, okay? If you have a function that's continuous over an interval from a to b, right? And the function, and there's like a value in between what that function equals at a and what it equals at b, then the function equals that value at some point, right? And that's that video. Pretty much all 1.16.
Hope it helped, and if you have any suggestions, please feel free to leave it in the comments. And if you like the video, please leave a like.